All right, I think we're good to go. Cool. Good morning, folks. Good to see all 50 of you here. Do we have the sheet, by the way, to pass around? All right. How are we doing? How's your weekend? I was fine, perfectly normal. Nothing was different about this week at all. So, all right, a couple of things I want to bring to your attention. Today is March 3rd. Dating system, 2026, 03, 03. Oh my goodness. Today, so a quick update. Homework 2 has now been posted. The shorter homework, okay? A lot less coding, but it's on optimization. Homework number 2 is posted, and it's a shorter homework. It'll be due next Wednesday, okay? Due March 11th at 5 p.m. on Canvas, okay? Again, just because it's shorter, do we start late? No, we don't. No, we don't, okay? Because it can get tricky, you never know. All right, specifically, it's going to be covering linear programming, okay? Meaning optimization with linear costs and constraints. I'm going to give you a bunch of constraints to add, and you're going to set it up as a linear program and solve it in MATLAB, okay? And that's due next week, all right? And give you a little bit of practice in optimization. Now, today, we are continuing on our topic of trajectory optimization, all right? I love trajectory optimization. It's probably my, I told you this, I probably haven't told you this story. It's my first experience as a researcher where I had to really figure something out on my own, like that even my advisor didn't know. Like I've just always been fascinated by the idea that I've sort of been fascinated by the idea of what if you had some system, robots, or it's a game, or power plant, or it's just or a sport. That you just define what you want, and an algorithm tells you what's best. I always thought that was cool, right? That's why I'm kind of in this business, right? And robots, on a good day, they'll do what you tell them to do, right? And you can see it come to fruition. That I wanted you to do that task. I defined the task, you optimized, and came up with a solution, right? Okay. Seems simple enough, especially considering, I had access to MATLAB as a grad student. I had access to our nonlinear solver. Anyone remember what the name of the solver is in MATLAB for nonlinear functions, for nonlinear constraints? What's that? fmin_con, right? I had access to fmin_con. I should have everything I need. It's got an optimizer. That's awesome. All I need to do is throw a simulation in there and say, hey, I want this to be as efficient as possible. I want this thing to be as fast as possible. I want this robot to walk as good as possible. But it turns out it wasn't that simple, right? I, just a wee baby grad student, I wasn't an actual baby. I'm not that smart, okay? But I was like, what do I do? Well, why don't I just put a simulation in the cost function and in the constraints and say, these are the constraints I want, the cost function I want, and I run it. I had accidentally done what we call single shooting, right? And it's makes the most sense in the world. You have the optimizer try something out, see how well it does, tries to improve the cost, tries to improve the constraints. Seems easy. And that's what we did last 2 coding streams ago, right? We did single shooting with the drag race, right? And it worked just fine. Simple problems, it works just fine. But as the problems get harder, we were starting to introduce things like multiple shooting, which were halfway through coding, 2/3, 3/4 of the way through coding the coding stream last Thursday, okay? I was a little tired, a little slow. Sorry, we'll go faster next time. Stronger coffee, okay? And multiple shooting was one of the first revelations I started to understand that hey, sometimes it's not if your optimization is just not working, which would happen to me in grad school. I put this optimization together as work, and it would say no. It would say converge to infeasible point. Local minimum not found. What? What's happening? What am I doing wrong? And the literature kept talking about this thing called multiple shooting. And I was like, why do I need multiple shots? Why don't I just do one simulation, you dum-dums? Why are you making it more complicated? And I should have listened to the literature that was telling me that, hey, if you have these problems that are hard to solve, sometimes you want to do multiple shots. And then you tell the constraint to say, hey, all the shots, they need to line up, right? And that's what I did one of my first papers on, was using multiple shooting for a particular problem, blah, 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 blah. And I loved it, right? But only then did I realize, like, I'm at the tip of the iceberg of really cool and crazy counterintuitive ideas in trajectory optimization, okay? So let's go back to our board right here, okay? So recall multiple shooting. Okay, it's a trajectory optimization formulation. Where are you? Evaluate costs and constraints. Using multiple time marching integrations. When I'm saying time marching, you remember Euler's method? You had to do this for your homework 1, where you start at time point 0 or whatever, move a little bit forward, you march using Euler's method or some other method. ODE 4.5 is also a time marching method. Why? It moves forward in time. Okay. I'd say, is there another way to move in time? Stay tuned. Okay. All right. So using multiple time marching integrations of the dynamics and aligning them with defect constraints. Does anyone remember a reason? What were examples of the kinds of systems that it was useful to have multiple shooting? Might be in your notes. You don't remember? Yes, Marco. Nonlinear, unstable systems, especially. Yes, absolutely. Absolutely. You could also say underactuated systems, which we very informally define. It's not part of the formal full course material, but there's a whole course on it at MIT, publicly available online. I've already talked about how awesome that course is. It's just very, especially if you have no background in robotics, or it's called underactuated robotics, but it applies to more than just robotics. So, all right, with defect constraints, just recall what that means. The idea was that you would have your input trajectory, U of t, those are your inputs, of course. And then you would have your decision variables, which would define your input trajectory. This would be for all of your inputs. If you had multiple inputs to your system, multiple motors, multiple pipe flow inputs, whatever it is, you would have one of these little input trajectories. Now, again, we tend to use splines, okay? You don't have to use splines. Splines are good, though. They're pretty standard, right? So those blues, those are decision variables, right? Okay, and to be clear, you could have any kind of spline connecting these points. Those splines connected by lines, call them linear splines because we're not creative. Okay, or first order splines because it's just a line. You could have quadratic splines and they go, whoa, shoot, no. They could go, whoa. Quadratic splines, that'll be second order splines. You could have zero order splines, which is this. It's flat. This is for the control input. You could just say, hey, I want it to be that, then that, then that, then that, and that. You could have cubic splines, which are order 3 splines. You can do 10th order splines if you're a masochist. Okay? Nothing's stopping you. Right? Those are your control inputs. And if you were doing single shooting, that's all you would need to define as your decision variables. But in multiple shooting, we did something fancy. Oh, that's not what I want. Black. Boop, 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 boop. Are you on the stream, by the way? Pull it up. It's probably fine. It's all good, but. Doing good TA work over there, DJ. Thank you for your service. All right. But for multiple shooting, okay, you also have decision variables for the initial conditions of each of your shots, okay? And what you do is you say, oh, I'm going to simulate, oh, and this is, by the way, x of t, of course, x of t. What's x of t, friends? It's our state. Yes, it's our state. 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 Make sure we're awake this morning. Thank you. Okay. All right. And the idea is we'd run a little simulation here for a little bit of time. A little bit of time, a little bit of time. I'm just drawing random little wiggles. Okay? But these, of course, these blues here, those are decision variables as well. We added more decision variables. And we added constraints that said, hey, when this is a real trajectory, a real continuous trajectory, our states can't jump. I can't just teleport, right? If you have discontinuous dynamics, it's a different story. But if you have continuous dynamics, as in, x dot of t is equal to f of x of t u of t, those are our dynamics in continuous time, right? Did anyone think of dynamics that are discontinuous? Nobody? Yes. Not a bad idea. So you're thinking discontinuous time. Let's say the time is continuous, but all of a sudden, your state can change instantly. Let's take my little thing that okay, this I have in my hand. This is my pen holder, okay? All right. How many states would I need to represent this system? Anyone want to guess? If it's just, sorry. I'm very coordinated. Okay, right? If I wanted to do the dynamics of the system, it would be 2 states this way, 2 states that way, 2 states that way, another 2 states for for yaw rotation, pitch rotation, 12 states, right? Position and velocity for each. Okay? Watch what happens now. Keep in mind of the velocity, which is a state. Think about that velocity. Was that velocity continuous? Or is it going down? Boop. Now it's going back up. Now, you could model that as being a collision, an instantaneous change in velocity. You took physics. You do the billiard ball problems, the one billiard ball hits another billiard ball. There's the instantaneous inelastic, the elastic impact, or even an inelastic impact. And all of a sudden the velocity changes. That's a sudden change in state. So that's an example of a discontinuous set of dynamics. So, which is pretty cool, because when we have systems where we have collisions, it's actually going to make our trajectory optimizations harder. Okay? You have to use different tricks for it. But anyway. So, but if we have continuous dynamics, this thing is flying through the air, wow, or I'm just moving it with my hand, wow. all my states have to line up, right? It's not teleporting. It's not instantaneously changing its velocity. So we have constraints that say that these must be equal. So we call these defect constraints. Okay? And one of the reasons that this works so well with multiple shooting is that as we make these shots shorter and shorter and shorter, while the dynamics are linear, if we make the time horizon, if we make the amount of time we integrate them for smaller and smaller and smaller, they become approximately linear. Okay? Which means that these constraints become approximately linear. We like linear constraints, right? Those are good. They get you closer to something like a quadratic program or a linear program. It wouldn't actually be a quadratic or linear program, but it becomes closer to that. It becomes easier to solve for F min con. Okay? So you have multiple shooting, or MS, adds additional decision variables for state specifically, and defect constraints. Saying that the end of this trajectory, that end of that little integration, must be equal to whatever that variable was. Okay? That's what we're coding up currently in our coding sessions. Continued on Thursday. All right? Okay. But you are still doing these time marching integrations. Okay? You'll have to simulate. So if your simulation takes time, your optimization is going to take time. You're going to have to try all these different methods. It's got to try off all these different values of decision variables and saying, okay, is moving this up good? Is this moving this down good? Using finite differencing to say, did this improve the cost? Did this, or did this worsen the cost? Did it make the constraints closer to being satisfied or not? So still need simulate many times if the optimizer is using finite differencing to calculate gradients. Again, that's when you change a variable just a little bit and you see how much it changes the output. And then rise over run, it is a calculate the derivative. Okay? You calculate derivatives. Okay? What if you didn't have to simulate the system at all? That's the correct furrowed brow. Christian furrowed his brow. That's what I did. That's what Christian furrowed his brow, a grad student. How can you assess how well this dynamical system is going to do over time if you don't simulate it? Okay? At least with a time marching integration. Okay? Well, my friends, let's enter the world of direct collocation. Okay? Going to use a lot of the same tricks as multiple shooting. That makes it better for your nonlinear or unstable systems. You want to swing up and balance a cart. Or you have a nonlinear system like a walking robot. That's unstable. That thing falls over all the time. Okay? But you want the optimization to not take forever. Okay? And honestly, make it more reliable. Okay? So direct collocation formulates a trajectory optimization, TO, okay, by representing the state trajectories as dynamics-free splines. You know what a spline is? It's dots connected by lines. Okay, but they have no dynamics to them. Okay. The dynamics are enforced by defect constraints on the slope of collocation points. Okay, that's a bunch of words. I like pictures. A toddler. Okay? What do I mean by any of that? Okay? So before we, with multiple, let's look back at what our decision variables are going to be for this trajectory optimization. And it's going to be a lot like multiple shooting. We are still going to add decision variables not only for our control inputs u of t, but also for our states x of t. So our control input will look like probably like a spline, where those blues are decision variables, right? DVs. Okay. However, and yes, we will also have decision variables for the state that the optimization can change, like any decision variable. But we connect them with splines. They don't need to be linear. None of these splines need to be linear, as I laid out before. Okay? Connected by splines. These look like cubic splines. What kind of spline? Well, that's a choice you get to make. And there are benefits and drawbacks to different choices, but they're connected just by magic lines, right? This is the evolution of our state. This is our physical system. This is this thing moving through space and time, right? Who's to say it's going to follow this magic line that we drew? It's just splines. There's derivative. There's no direct dynamics there. It's dynamics free. But then what we do something interesting. We then look in the middle of each of these spline points, in the middle, in time. Okay? Then we look at the slope of the tangent line at those points. Slope of the tangent, right? Okay. Well, at those particular points, slope of that tangent line, okay, that's going to be that slope, that's rise over run. Rise over run is change in rise over change in run. So the slope there, here, that's going to be some delta x of t, delta x over delta t, rise over run. Delta x over delta t, what is that like in calculus? If I were to write a calculus version of that, what would that look like? dx dt equals dx dt of t, or as we cool people in this class call it, x dot of t, right? That slope of that line, that's approximately x dot of t. Okay? Interesting. Let's go back to my definition. The dynamics are enforced by defect constraints on the slope of collocation points. Well, x of t, don't we have an equation for, sorry, x dot of t? Don't we have an equation for x dot of t? Our dynamics. That x dot of t is also equal to that f of x of t u of t in state space form. That thing we spent like a week or so doing at the beginning of class, right? Anything you want to simulate, you got to put in that form, right? You have those equations. So we enforce a defect constraint that says at each of these lines, each of these slopes, make it green for transparency here, each of those slopes must equal our dynamical equation, or whatever x of t is or u of t is at that point. But what's happening is that our optimization is drawing an imaginary magic line saying, oh man, wouldn't it be great if my trajectory could move like this? But then these defect constraints are saying, Once you have solved the problem, though, each of these slopes has to follow physics. Okay? It's actually kind of cool. If you watch the iterations of a direct collocation formulation going through the optimizer is going, try this, 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 try this. And then you plot what it's trying, you will see it like, I want to get from there to there, and it'll go, zounk. It'll get there, and then it'll start massaging out the curves to make it look like physics. It's really cool, okay? Let me write this out, okay? So we add defect constraints, and let me also label this. These are called a collocation point. C-O-L-L-O-L-O-C, collocation point. Okay, co-located. Okay, it's halfway in between those points right there. So we add defect constraints that require the slope of the tangent at each collocation point equal the system dynamics. Okay? And here's the kicker, because this all might seem wacky. Is this a little wackadoo for someone? Anyone want to admit that's wackadoo? Okay, you're all smarter than me then. I thought it was wackadoo. Do this. Here's the beautiful thing. This constraint, where we say that the slope delta x delta t must equal that, we don't have to simulate at all to know if it obeys that. We just, this equation, which was just like, we use some math to figure out what the slope is at that point, just algebra. We've already derived this equation. We're doing any kind of simulation. That's just math. You don't have to integrate anything in order to check that. That's pretty cool, no simulation. And further, my friends, what if we wanted to know the derivative of that constraint with respect to our decision variables, our gradients, our Jacobians? We can just take them analytically. No finite differencing required whatsoever. You can still use it if you want, by all means. Not always a bad thing to do. You don't have to use finite differencing, which means you don't have to run these functions so many times. And guess what? In MATLAB, they have an option, like many solvers will, that you can say, hey, don't worry about calculating the gradient yourself. Don't worry about calculating those derivatives. I'll give them to you. Save you the time. That's what we're going to do in class, in these coding lectures. So it's faster, a lot faster. And the derivatives, they're not even approximated. They are exact. Okay? Finite differencing is a guess, so it's an approximation of the derivative. I'm giving it an exact derivative. That means the solver can be more reliable. How reliable is it? How good is it? Well, let me see if I can actually do this correctly here. So yeah, so here's an example from my postdoc days. So we had this big old robot here. I know you've seen this video before. This is a robot with some absurd physics in terms of the size of the equations. If you were to print out the equations for it, they would take several football fields. Okay, we use Lagrangian mechanics to derive it, which, by the way, we'll also learn in this class. A little aside, a little bonus in optimal control. You learn Lagrangian mechanics. We know Newtonian mechanics. F equals ma. Nods. Can I get any nods? Oh, Christian's nodding. He's paying nods. F equals ma. Yes. Okay. Yes. We all know F equals ma. Lagrangian mechanics is just a slightly more complicated formulation, but it's really good for these more complicated systems. There's even better methods. Actually, I'm teaching advanced dynamics in the fall round. Is that on the course list? Do people see that? You're nodding. It's on the course list. There was some confusion. I'm teaching advanced dynamics as far as I'm aware, okay? And anyway, I'm going on an aside. There are lots of cool ways to do dynamics. So neat. But here, this robot, we wanted to know how to walk efficiently. So we set up a trajectory optimization problem using direct collocation. And we just gave the derivatives to an optimizer. We used a specific optimizer called IPOPT, IPOPT. It's like a sort of souped up version of fmincon. It's really good for big problems, but it's free. It's online. You can find it. Okay? And what came out when we ran the optimization were all these trajectories. Okay? And despite how complicated the physics were for this robot, this took a couple minutes to run. Okay? And you can see each of those little things just so you can see what we're looking at here. You can see on one axis is like an angle, and on another axis is a velocity of that angle. You know, theta, a phi and a phi dot, theta, theta dot. I'm plotting there, right? Those are trajectories that we gave to each of the motors. And we said, oh, at each point in time, try to track those trajectories with a PD controller, something we all know how to code. Okay? And then the result was this, okay? It walks. There was more to it than that. There was we had to add an outer level, an outer layer of feedback control to make sure it kept staying up, because the trajectory was just a feed forward trajectory of the joint angles that we wanted. But if it was falling to the side, we told it to kick its leg out a little bit. If it falls to the other side, kick the leg out a little bit more. If it's tilting, pull the leg in. Yeah, that's why it's kind of got a little hitch to its step, a little bit of feedback control. Okay? And we were telling it to minimize the amount of energy to walk. And the consequence of that is we had this really smooth human-like gait. We didn't tell it have a human-like gait. It kind of just came up with it because it's just efficient. Robot, right? But this was only possible because of direct collocation, right? Oh, look, I was such a baby. That's me on the second from the right, okay? Such a baby. What time has wrought. All right, let's go back to. So let's go. We need more details. Any questions so far? Because we're going to do some more details of direct collocation. Okay, good. Okay. All right. So let's talk about strengths and weaknesses here. We just talked about how it's great that we can. So advantages. Okay. Does not require time marching integration. Time marching integration. You can provide exact derivatives. Okay? The result of this tends to be faster and more reliable to solve. Okay? Those are some advantages. Can anyone think of any disadvantages of this approach? Anybody? It's magic, it's perfect, there's nothing wrong? I wish. Nothing like that in engineering or life. Well, we're approximating the trajectory as this magic spline. And yes, we're checking it at these points to make sure at those points it's obeying physics. But elsewhere, we don't know for sure. Right? It's an approximation of the state trajectory. So it's not quite accurate. It actually sacrifices some accuracy of your simulation to get this result. Okay? Sacrifice accuracy of the state trajectory. Okay? A lot of times, that's okay. Because in real life, the physics that you derive, there's going to be some discrepancy between that and real life. We make these assumptions all the time. We assume there's no air resistance in the room, right? Pretty good assumption to make. Not bad, right? But it's true. There is air resistance. There are all these little things that you don't model in your physics. So it's going to be wrong anyway. What if it's just a little more wrong? Who cares? You know? And specifically, if you're dealing in the field of control, which, guess what? That's all you. You probably have to put a feedback controller on it anyway, in case it gets bumped, right? So there's already going to be what we call some robustness to some error if we have a good controller. Like, we could not count on that robot not having a feedback controller. It's going to fall over, right? So who cares if the physics are just a little bit off? And if you need them to be more accurate, you can just add more and more points along the way, right? Who chooses the number of points that we have? We do. The more points we choose, the more collocation points we're checking. We're checking further and further along the trajectory, right? It's going to be more and more accurate. Okay. All right. So, I'll say just to make we'll save that for later. Okay. Let's talk about approximating the state trajectory. With splines. Okay? Because who gets to choose the type of spline? We do. We get to choose. But that choice of what kind of spline we choose actually determines the type of integration we are approximating. What do I mean by that? We'll say, an example, assume a linear state spline. Okay? Where we have x, we have t. We're going to have decision variables that are optimization controls. They are in blue. Okay? These are for the state because this is a direct collocation problem. We have to have decision variables for the state. We have a linear state spline. Okay? Okay? Then we're going to look at the collocation points in the middle. Okay? And let me write the dynamics. Our dynamics are going to be x dot of t is equal to f of x of t, u of t. That's just saying that how much our state is moving, depending upon our current state and our control input. That's what we've said many a time. Okay? Now, my friends, let's also have let's have a constant series of points let's say they're separated by delta t. Okay? But here I want to introduce a very common, a common notation. The time step delta t we'll often call h. That's just standard in the literature, h. Okay? So if I use the letter h, it's just the time step delta t. Okay? Now, this collocation point, we need to check the slope of the tangent line of the spline at the collocation point. Well, my friends, this one's easy. It's just that exact line, right? The tangent line is that. That's the spline. Okay? So our slope of the tangent here, delta x over delta t, okay? That's going to be, and we'll call this here, this variable, we'll call this, in blue, we'll call this, each of these we'll call them xk, where k is the number, that's the point number, or the not number, or like basically the number, like this is number 1. That's number 2, that's number 3, okay? So our slope, delta x, delta t, that's rise over run, right? Well, what's the rise? That's xk plus 1 minus xk. That's rise. What's run? Delta t, for h. Following me so far? That's the slope of the tangent of a spline. Okay. Any questions about that? That's just slope. Well, good. Now, I'm going to solve, my friends, for x of k plus 1. Well, x of k plus 1 is going to be equal to, I'm going to multiply this by the other side, then put xk on the other side. It's just x of k plus delta x, delta t times h. Does that look familiar? Saw flicker recognition on 2 people, 3 people. Anyone remember that? Yeah. Yeah, it's y equals mx plus b. That's true. In the terms of integration, we had a method. It rhymes with Spoiler's method. Euler's method, yes. Great-granddaddy rears his head again. Okay? Saying that, hey, the next state is equal to the previous state plus the rate at which the state is changing, your dynamics, times change in time. That's Euler's method. Right? Because right, this right here, that's approximately x dot of t, right? So, but the fact that we chose a linear spline, it means we're using Euler's method. Oh, interesting, my friends. Okay. Now there is some choice. So basically, you just got to plug in x of t. All right. And if we have that as our dynamics, which we do, right there, the only question is, we do get to, so you might say, well, this is perfect. All I got to do is find what is my x dot at that point, and then that creates my defect constraint. And that is Euler's method, particularly what we call forward Euler's method, because we're getting the next state based upon the current time, derivative at the current time. Okay? So let's call this forward or explicit Euler. Okay? is that xk plus 1 equal to xk plus the derivative of our state, which you'll recall is that this is this thing up here, right? These are your dynamics of, so that's just f of xk u of k times h. These smiles, are they good smiles or are they confused smiles? That's Euler's method from before, right? But this is specifically a defect constraint. Constraint. It's an equality constraint. You can enforce. You must enforce at every collocation point. Okay? So we add a bunch of constraints to our problem, and they're written like that. And of course, they're equality constraints because if, as guys will note, there's an equal. All right? That's forward explicit Euler. Interesting. We kind of fell backwards into Euler's method again. Right? Just by using this fancy method called, this fancy approach called direct collocation. Okay? You might note I have somewhat forebodingly called it forward Euler. I'm sure someone in the audience is like, is there a backward Euler? Maybe there is, I say forebodingly. Maybe there is, but what would such a thing, what would that be? I mean, you have your previous state, your next state is equal to your previous state times your current derivative, because of xk, times your delta time step. What else could you do? You don't know the future. It's not like you could say xk plus 1. What's the next derivative? Wait, sure we can. Xk plus 1 is just the decision variable that we have in our trajectory optimization. We can use the future to inform the past. That's pretty cool, right? You can't do that in time marching methods, right? You have to start here, forward in time, keep going, keep going, keep going, keep going. But because in our decision vector we have all these values for what we guess currently are the states in the future, why not use those? It's actually better. So backward or implicit Euler. See how this is getting weird now? We're using the future to inform the past in these trajectory optimizations. It gets weird, but it's amazing. Backward implicit Euler. It's very similar. It's an Euler's method. It says, hey, the next state is equal to the previous state, but we're going to use the derivative from the future. Oh, so uk plus 1, sorry. So we want to use uk plus 1, that's the next time step, and uk plus 1, xk plus 1, uk plus 1 times the time step. I mean, these are just variables in our decision vector. Why not use them? Okay? These implicit methods use the future. It's still a linear spline. It just uses a different estimate of the slope. You say this is a more stable and accurate integration. We can use it actually. So you might recall we did examples of Euler's method with a pendulum, where the pendulum went crazy because the physics were bad. It's an approximation. This is a better approximation. It can still go wrong, but it's better. That's with the linear spline. But you're already starting to, I imagine some people are starting to wonder, it's like, hey, if I can use the future to help inform my slope, hey, maybe I could use, like, what if I use the past and the future together? What if I average these two estimates of our slope? Maybe that's better. Okay? Well, in fact, if you kind of think about what that integration looks like, so let's say, so let's just write it. I'm going to leave some intentional blank space because, you know, for dramatic effect. Okay? Dramatic effect. Where we're going to say that xk plus 1 equal to xk plus 1/2 f of xk uk. So that's the current time point, plus the future time point. And we're averaging them times h. This is an average of the two, right? Well, if you take an into the proximate integral as the average between two points, remember that from calculus 2, called trapezoidal integration. Okay? Trapezoidal. Sometimes called, that's a parenthesis, Crank-Nicolson integration. Integration. Even better, even more accurate. But I'll point out, this is no longer a linear spline. You actually see what this looks like. Keeping in mind, we have, here's x of t, here's t, here's all of our points. Okay? It means that in between so here's our collocation point right there somewhere. Let's see, where is it? Okay. Our collocation point there and there, wherever they are, okay? The slope of the tangent at that point is the average of the two other of the dynamics here and here. Okay? So it's like your spline is actually quadratic. So it becomes a quadratic spline. Okay? So if you use a trapezoidal method, you are implying the spline is quadratic. Okay? And hey, wouldn't a quadratic spline be a little bit more accurate than a linear spline anyway? It's curvy, to use the technical term, right? So you might say, oh, I know where this is going. Cubic splines. Yeah. There's a method for using cubic splines. Oh, cubic splines, okay? Called Hermite-Simpson. It's a little bit more complicated because as you add more terms to a polynomial, there's more coefficients to define. You actually have to make some more, you have to add some more constraints, okay? The Hermite-Simpson for a cubic integration. The formula gets a little bit more tricky. The only thing that you got to note is that we have to think about a couple of things. We got to think of x of t and t. And yes, you will have your decision variables at here, where this one is xk, this one is xk plus 1, or x1, you know, it moves on like that, right? With a difference of h in the middle, of course, right? But with a cubic spline, we'll kind of draw a little Hubicki spline. Sure, why not? Perfectly cubic, don't question me. Okay? You have your collocation endpoint in the middle. Okay? Okay? In order to fully define the cubic spline, we actually need a third point for your decision variables. So we call it xk plus 1/2 in the middle. Okay? And you have two constraints here. Say that, hey, the xk plus 1 equal to xk type plus 1/6. We'll call f of xk uk. We'll just call it fk. Just get rid of the xk uk, make it a little thinner. Okay. Plus 4 times f of k plus 1/2 plus fk plus 1. So you can see this is kind of like a weighted average of the point at one end, point on the other end, and a point in the middle. This just falls out if you do the math of the slope of what a cubic spline looks like. Okay? All right? And you have to tell it that, hey, x of k plus 1/2, it is equal to 1/2 times x of k times xk plus 1 plus h over 8 times the quantity f of k minus f of k plus 1. And to be clear, we're going to say that fk, what that means is just f of x of k, u of k. Make my life easier. F of k plus 1 is, of course, f of x of k plus 1, uk plus 1. All right? That's Hermite-Simpson. It's cubic. What's the benefit of that? Smoother. It can do more wiggle wobbles, again, to use the industry standard term, which means it can fit the actual real life physics a little better, right? I mean, my crazy, wacky, wailing robot with, waving robot with the purple robot that we were all working on, okay? The physics of how the position is going to change over time are not going to be perfectly quadratic or perfectly. It's going to be following some weird trajectory that physics are deciding. But the more terms we add to that polynomial, the more we can fit it to what actual physics is happening, right? Okay? I will say, in practice, I tend to use the most trapezoidal. Okay? I tend to use that the most. Doesn't add a lot of complexity to the constraints. Okay? And if you want it to be more accurate, I just add more points. That's what I do. Okay? All right. Let's do an example. So let's do an example. Do the drag race problem using direct collocation. We have my super sweet automobile sliding along without friction. It's got some control input u of t right there. It's sliding. We want to get from there to there and come to a stop, even though I understand it's not required, just suggested that you don't drive forever. Okay? Right. So let's write the decision variables, decision vector, cost, and constraint for the minimum time. The fancy word for this is the double integrator, but drag race sounds cooler. using direct collocation with explicit Euler integration. Integration. Okay. What we're going to do is we're going to say we have n spline points. Okay. We know that our physics, x of t, has some distance, s of t, s dot of t in its state vector. And the derivative, x dot of t, and this many a time, the derivative of our first state is our second state. And derivative of our second state is our acceleration. Because we're all physics experts, we all know that it's 1 over m times our force, u of t. Okay? Look how smart we are. Fantastic, great, cool, awesome, neato. All right. Then we have that. We have n spline points. Those are our dynamics here. Okay? Now we need our decision vector. Okay? My decision vector, w, is going to have all of my control inputs. So u1 through uk up to un. And I'm going to need decision variables for all of my states across the trajectory. It's going to be s1 through sk up through sn. Do we have any more states to worry about? How many states do I have? 2. Okay, what's my second state? What's my, yes, the s dot of t. Thank you. I'm going to lose you at this early hour. You got so much more day left in you. Okay, all right. I'll just call it ds. So ds1 through dsk through dsn, the last one. And because it's a minimum time problem, I'm going to say the total time is also going to be a decision, right? That's what we did in our single shooting problem. It's going to be our total time. Okay. Our cost function, one of the easiest cost functions imaginable. I'm calling it J of W because F is already taken, my friends. All right? Minimum time. What am I minimizing? Time. Time. Now the constraints. This is where the rubber meets my money and the rubber hits the road, or whatever it is. Okay, so our constraints. We want to make sure that we have our final state. So we have our final states. We want it to start at rest. We'll do our initial and final states. States. So S1 equals 0, ds1 equals 0. That's easy, right? Start at rest, start at 0. We want it to stop at some final time. Sn is going to be at some s final, where we want it to stop. And dsn, the velocity, is 0. Okay? We're good with there. Okay? We can do force limits. That's going to be an inequality constraint. We could say that all of our u's for uk is greater than some u min and less than or equal to some u max. Well, that's easy. Okay, great, awesome, cool. The only thing we're missing is physics, that small detail. Now we need our defect constraints. That's where our physics come in. In direct collocation, physics is only enforced by the constraints. There's no simulator. This is what grounds your trajectory optimization to reality, right? Because we're using forward or explicit Euler, that means for every state, xk plus 1 is equal to the previous state, xk, plus the derivative of the at the current time and state, x of k, u of k, times delta t, or h. H. Now our state is, of course, s k plus 1 and ds k plus 1 in a little vector is equal to our previous state, which has s of k and ds of k plus f of xk uk. That's our physics, which you can scroll up and see was dsk and 1 over m uk times h. Okay? Well, if you want to compute what h is, I'm going to scroll up. I'm going to draw a little. Well, let's scroll down. What's h? Well, if we have our time and we have our state here, here's our final time t, and we have n points, 1, 2, 3, 4, 5, 6, 7, 8, up to n, right? We have n points. Call this one, we'll call that Tn. Then what is the size of h? Algebra. That close. It's not quite t over n. T over n minus 1. Because while there are n points, 1, 2, 3, 4, 5, 6, 7, 8, n, that's why I learned how to count in school. There are n minus 1 gaps between those points, right? If I have 10 fence posts, there are 9 connecting posts between those fence posts, right? They call that the fence post problem. We're so clever, okay? So that means that h is equal to t over n minus 1, which means that this is t over n minus 1. Right? Boom. Those are your defect constraints for all k from 1 through n minus 1. Again, n minus 1 because we won't have to connect the second to last one to the last one. We don't need to go past the last one, right? Because otherwise we'd end up with an extra value at the end. That's it. That's direct collocation. We set it up where, hey, we have our decision vector, our cost function. So easy. Initial and final states and limits. That's easy. Now we have to make this constraint for every k through 1 through n minus 1. Give that to the solver, and it is shocking how how fast it can be. Right? Question? Yeah. If n is 1, you're not even simulating a trajectory anymore. There's not even you only have 1 point, right? So this math will fall apart, and I'll cry. Thank you. I appreciate your thoughts. You're sparing me my feelings. Yes, I appreciate that. So yeah, n will never. There's no reason you would ever make n 1. Other questions? Here's the other thing. You know that initial guess that we have to give our nonlinear solvers? So far, we've been able to give it pretty silly initial guesses. But as the system becomes more complicated, you'll start realizing, oh my goodness, I need a better initial guess, or it's just not going to work. It just says No solution found, no solution found, no solution found. What's happening? Well, there's no guarantee that any nonlinear optimization is going to work with fmin con. But direct collocation is so much more robust. Bad choices of initial. For the big purple robot called Duris, we gave it garbage initial guesses. We gave it random numbers. They came up with that walking mode. Okay? That's all I got for you today. Thank you all so much for coming. Homework due Wednesday at 5. Shorter homework, okay? It should be posted online. Oh, thank you.